On October 28, 1943, at the Philadelphia Naval Shipyard, a United States warship was said to have vanished from the water, then reappeared far away in a blink. People later gave the story a name, as if naming it could make it real. The Philadelphia Experiment. In the version passed from mouth to mouth, the ship didn't only become invisible, it slipped somehow out of time. The crew were described as trapped between moments, caught in a misfired kind of time travel. The Navy has denied it for decades, and historians tend to file it where myths go when they wear a uniform. But the persistence of the tale matters, because it reveals something human. We don't chase time machines only for wonder. We chase them because we want revisions. A sentence we wish we never said. A door we wish we had opened. A night we would pay anything to rewrite. Yet while legends and films keep drawing time as a road you can drive backward, one physicist asked a stranger, more practical question. Richard Feynman, raspy voice, mischievous smile, wondered why the past can feel gone and still refuse to leave us. This is not an attempt to unlock a secret hatch back into 1943. It's a walk through Feynman's way of thinking. Cups that shatter, ink that spreads in water, and the quiet authority of thermodynamics. If you stay, you won't just learn why a broken glass doesn't reassemble itself while the equations can run either direction. You'll also see why the universe had to begin in an almost unnaturally tidy state for memory, history, and the felt one-way flow of time to exist at all. And by the end, you may discover the real answer to the question you've carried for years. Can the past ever truly come back? It is tempting to believe that if a ship can vanish once in a story, then there must exist some hidden door where whole days and whole lives can also step out of the timeline. To see why physics refuses to grant that door, it helps to walk back for a moment to that foggy dock in wartime Philadelphia and watch the legend assemble itself. In the most popular versions, the destroyer escort is wrapped in cables, generators hum, a strange green haze rises, and then the ship is simply not there. Later it reappears somewhere else, sailors confused, some said to be fused into the metal itself. The details change from teller to teller, but one element is constant. The ship does not just change location, it is said to slip out of time, as if time were a river and someone briefly lifted the vessel, carried it upstream, and put it down again. That picture did not begin with that story. It is the same picture that powers almost every familiar time travel film. When a film like Back to the Future reached cinemas on July 3, 1985, it did more than launch a franchise. It took an old intuition and gave it a bright, mechanical body. Time as a road, marked with dates instead of distance, and a car that can go forward or backward, depending only on which lever you pull. In that picture, the past is a region you can revisit, if your technology is good enough, or your magic is strong enough. You drive back to 1955, change one conversation or one accident, and then return to find that the present has rearranged itself to match the new history. The plot hangs on regret and repair. If only the right person arrives early enough, the worst things can be undone. People accept this structure very easily. It speaks directly to specific kinds of human regret. Words that should never have been said. Chances that should have been taken. Accidents that feel as if they ought to have been preventable. A timeline that can be driven backward offers a kind of conceptual compensation. If you cannot repair something now, perhaps a more advanced civilization or a better machine could go back and repair it for you. At the level of ordinary experience, though, time behaves in almost the opposite way. A glass slips from a hand, hits the floor, and breaks. A bowl of soup spills onto a shirt. A sheet of paper is torn in anger, and the fibers do not knit themselves back together after the mood passes. Someone says a clumsy sentence in a meeting. They can apologize later, but the sentence has already contributed its bit of structure to the room. In all these cases, nothing important has disappeared from space. The glass fragments are still there. The soup is still on the table, in the cloth, On the floor, the paper is still in the room, only no longer in a single piece. The sound waves from the sentence have carried energy into the air, into the walls, into the eardrums of the people listening. Yet the intuitive verdict is that something has crossed a one-way line. There is a before and an after, and only one of them can be inhabited. This is the first puzzle Richard Feynman liked to circle around. At the scale of humans and kitchens and streets, time points. It has a clear orientation. Cup whole, cup broken. Desk neat, desk messy. Body young, body older. The direction is so reliable that people use it to organize memory and blame and responsibility. You never see the opposite process outside jokes and special effects, so you build a life around the assumption that it will not happen. The legend of the vanishing warship and the fantasies of time machines all cut against this background. They suggest that the orientation is not fundamental. They promise that with enough power or cunning, you could bend the arrow back on itself and walk against its direction. In that sense, even conspiracy folklore quietly agrees with high-budget science fiction. Both insist that the rules you think you know are probably not the deepest rules, and that someone, somewhere, is already circumventing them. Long before digital editing, people had already discovered how satisfying it is to watch the arrow of time run in reverse. In the late 19th century, camera operators for the Lumiere company filmed a simple scene. Workers swinging hammers against a wall. Bricks falling outward, dust blowing into the air. The short film was called Demolition of a Wall. Then they ran the frames in the opposite order. The dust flowed back into place. Bricks leapt upward into a neat pattern. The demolished wall, on screen, healed itself. When audiences in 1896 saw the reversed version, they laughed. They were not confused. They did not mistake it for documentary evidence of a real wall reconstructing itself. They recognized it as a trick and enjoyed the trick precisely because it violated something very familiar. That reaction is already a kind of experiment. It shows that even without formulas, the human nervous system has strong expectations about what counts as a normal sequence of events. If you watch a wall build itself in reverse, or a shattered plate reassemble in mid-air, you do not need training in thermodynamics to spot the wrongness. Everyday life has already trained you. Traffic does not spontaneously organize into perfectly smooth flow after hours of congestion without some additional cause, like a change in rules or behavior. Milk stirred into coffee does not unmix and climb back into the bottle. Ice cubes in a room-temperature glass do not absorb heat from nowhere and reappear fully formed after they have melted. So, something in experience tells a clear story. Time has a built-in orientation. It is not just that we remember earlier states and anticipate later ones. It is that we can look at a still photograph and often tell which way the arrow is pointing. A bedroom whose clothes are all stacked and folded feels like a plausible before. The same bedroom with clothes thrown around, dust on the shelves, and an empty glass abandoned on the table feels like an after. Without anyone adding captions, you can assign these labels. That judgment is not about emotion. It is about structure. In one state, the pieces of the room occupy only a small fraction of all the possible arrangements they could have. In the other, they occupy a much larger fraction. You may not consciously count possibilities, but your nervous system does something equivalent. It recognizes that the neat configuration is statistically rarer and tends to appear earlier in a sequence of actions, while the messy configuration is statistically more common and tends to appear later after many small disturbances have accumulated. Culture, meanwhile, keeps offering stories where this basic fact is negotiable. Films and novels show timelines splitting and rejoining. Characters leap from one branch to another. A few careful actions in the earlier branch produce a radically different later branch. The central device is always the same. Time is treated as a dimension like length, and the task is to move along that dimension in an unusual direction. Your body, however, keeps pushing back with a different message. Whatever happened yesterday cannot be undone in the way a scene can be reshot. You can change what happens next. You can alter how you and others interpret what happened. But the physical record has already begun to spread into a vast number of degrees of freedom. Atoms in the air, patterns of wear on objects, electrical changes in nervous systems. There is no button on the wall that isolates and reverses all of these at once. This clash between cultural images and bodily experience is important. It shows that people live with two almost incompatible pictures of time at once. One picture, favored in stories, treats time as a road with two open lanes. The other picture, forced by every irreversible accident, treats time as a slope you only slide down. Richard Feynman's interest lay in neither picture by itself, but in the tension between them and in the precise place where that tension resists simplification. When he pointed at a glass of spilled wine or a cloud of cigarette smoke and asked why it never spontaneously regathers, he was not being rhetorical. He was asking for a description that could, in principle, be written in equations and tested against the behavior of real molecules. By the end of this chapter, there is a working, intuitive definition available. The arrow of time is not a mystical force, and it is not a built-in label on each moment. It is the pattern by which states that are rare and constrained give way to states that are more typical and less constrained. It is the reliable observation that things tend to move from arrangements with fewer microscopic possibilities to arrangements with more. You do not need to compute anything to use this definition. You look at a sequence of frames and ask, in which direction does complexity spread, patterns blur, contrasts soften, distinct shapes dissolve into noise? That direction is what people ordinarily call from before to after. It is the same direction in which your own memories accumulate and in which your own body ages. The deeper surprise will only arrive in the next step. When a physicist like Feynman writes down the basic laws that govern the motion of particles and fields, those laws do not contain a built-in instruction that says, run only in this direction. They work, in almost every important case, just as well if you reverse the sign of time. That is the contradiction waiting at the edge of this first picture. Everyday life insists on a stubborn arrow. The equations, taken literally, seem almost indifferent. The contradiction between a law that can run either way and a life that clearly does not becomes clearer if you follow Feynman into a room built for chalk. Imagine a November afternoon in Cornell, in the middle of the 1960s, a blackboard already crowded with symbols, and Feynman turning to the students with a grin as he sketches simple arrows along a line. Then he waves a hand at the drawing and says, in his casual way, that if he films a bunch of particles moving under the known laws of physics and you later project the film backward, no one looking only at those particles would be able to tell which way is supposed to be the past. He is not talking about anything exotic. Think first of two smooth balls sliding on a frictionless table and colliding elastically. In one version of the film, they approach, touch, and fly apart. In the reversed version, they approach along exactly those outgoing paths, meet, and depart along exactly the incoming paths. Each frame satisfies Newton's laws. The only difference is the order in which you watch them. The same is true for two massive bodies orbiting each other. In one direction, they sweep out their ellipses counterclockwise. In the reverse direction, they sweep out the same ellipses clockwise. The gravitational law that tells you how the force depends on distance does not complain. It connects the positions and accelerations in a way that does not single out a preferred direction in time. If you did not tell an observer which reel was which, and if all they could see were those paths, there would be no mathematical mark that says, this is forward. And $25 in. Take charged particles moving in an electromagnetic field. Their trajectories are curved by electric and magnetic forces. The field responds to charges and currents in a way encoded in Maxwell's equations. If you flip the sense of motion and adjust the fields appropriately, the same compact set of equations remains satisfied. In more formal language, you can replace time by its negative and reverse the velocities, and the structure of the law remains unchanged. This is what Feynman wanted his students to feel in their bones, that many of the elegant equations written on the board are almost indifferent to whether you label increasing time as toward the future or toward the past. Classical mechanics has this property in a nearly exact way. Maxwell's theory of light has it in a more subtle but still real way. Even the standard form of the quantum mechanical law that governs the evolution of a wave function can be made to respect a version of this symmetry if you accompany the reversal of time with complex conjugation. Now set that beside the earlier kitchen scenes. A glass falls and shatters on the floor. If you film the event and then run the frames backward, the same mechanical laws could in principle be satisfied. The pieces could fly upward along exactly those paths, join with exact orientation, and end in a whole glass sitting on the table. At the level of individual molecules and collisions, nothing forbids that pattern. Yet your eye and your experience immediately reject the backward film as artificial. Something in your background expectations insists that only one of these stories is compatible with the usual flow of reality. Replace the glass by the orbit of the Earth around the Sunday. If you watch an animation of the orbit running backward, nothing in your intuition rebels in the same way. You may notice that the direction of motion has been flipped, but it does not feel as though a taboo has been violated. The path is still a smooth ellipse. The gravitational force still points inward. All the mechanical relations survive unchanged. It is like watching a pendulum swing in a mirrored room. This difference is already a hint. Some processes, when run backward, are merely unfamiliar. Others, when run backward, strike you as physically wrong. Yet the same underlying laws are supposed to govern both. The tension pushed Feynman again and again toward the same question. If the basic rules allow films that run either way, where does the everyday arrow come from? The one that points from memory toward ignorance, from youth toward age, from neat arrangements to scattered ones? To underline how little the abstract equations care about temporal direction, he often pointed to an event that took place long before those Cornell lectures. On May 29, 1919, two expeditions stood ready with cameras on either side of the Atlantic. One group was on the tiny island of Príncipe, off the West African coast. The other was near Sobral in Brazil. They were waiting for a total solar eclipse. During those few minutes, when the moon would cover the sun, faint background stars near the solar limb would become visible. Their apparent positions could be measured and compared with their positions when the sun was elsewhere in the sky. Einstein's general theory of relativity, only a few years old at that point, made a very specific prediction. The mass of the sun should curve space-time. Light passing near it should follow curved paths. The apparent positions of the stars during the eclipse should therefore be shifted by an amount that could be calculated in advance. The expeditions took their plates, the data were analyzed, and the observed shifts matched the prediction within the uncertainties of the measurements. It was one of the most celebrated tests of a theory in the 20th century. The important point here is not the drama of the confirmation. It is the character of the underlying equations. The field equations of general relativity are still local, differential relations between geometry and matter. They say how curvature and energy are related at each point. They are not built around a preferred orientation of time. The calculation that leads to the bending of light cares about spatial directions and null trajectories, not about which end of the eclipse sequence you call before and which end you call after. Garm, end quote. So on the one hand, there is a history in which abstract equations written down on paper in a study in Switzerland predict, years later, a subtle pattern in the heavens over Brazil and an island off Africa. On the other hand, there is the almost trivial fact that a cracked plate in a cafeteria will not reassemble itself while you watch. Both scenes are entirely real. Both are described by physics. Only one of them seems to respect the intuitive arrow of time in a way that you can feel in your own life. Feynman refused to let the contrast stay fuzzy. He kept insisting on clear examples where the laws themselves do not care. In a simple Newtonian system of balls, if you know the positions and velocities at one moment, you can compute both what they were an hour earlier and what they will be an hour later, at least in principle. The mapping goes both ways. If you flip the sign of the time coordinate in the equations and reverse the velocities, you recover another valid solution. Nothing inside the law marks one direction as preferred. A similar statement holds in standard quantum mechanics. The mathematical object that encodes probabilities, the wave function, evolves in a way that is reversible. If you could isolate the system perfectly and keep track of all its phases, you could, in principle, recover a past state from a future one. In actual practice, you cannot do this for more than very simple systems. But the structure of the law allows it. To show that this is more than a formal trick, experimentalists in the 1970s designed clever demonstrations in which a small piece of a system is made to behave as if time has been reversed. One of the cleanest examples is known as spin echo. The setting is a solid in which the nuclei of the atoms behave like tiny magnets. When placed in a strong magnetic field and tipped by a short radio frequency pulse, these nuclear spins begin to precess, like tiny gyroscopes, and their collective motion produces a measurable signal. At the start, many of the spins point nearly in the same direction in the plane perpendicular to the field, so their contributions add up coherently. As time passes, differences in the local environment cause slightly different precession rates. The spins fan out around the circle. Their phases become scrambled. The net signal decays, even though each nucleus continues to precess according to the same underlying law. Now comes the trick. After a certain waiting period, another radio pulse is applied, designed to flip the orientations of the spins in just the right way. After that pulse, the spins that were leading now lag, and those that were lagging now lead. If the system is sufficiently well isolated, the fan that had spread out begins to refocus. At a later time, the spins once again line up, and the net signal reappears as a sharp pulse. It is as if the microscopic movie of their relative angles had been run backward for a brief interval. Nothing supernatural has occurred. Energy has not flowed uphill. Entropy in the universe as a whole has not decreased. But within this small, controlled subsystem, the experimenters have engineered conditions that effectively reverse the microscopic evolution for the degrees of freedom they care about. The spins retrace their path in phase space. A pattern that looked as though it had faded into noise comes back into view. For Feynman, experiments like this were valuable not because they suggest a practical time machine, but because they dramatize the central logical point. If you know the detailed state of a system and the exact law that governs its evolution, then the distinction between predicting the future and reconstructing the past is, at that level, one of convenience, not of principle. The same rule carries states into states in both directions. This perspective can be unsettling to someone who is used to thinking of time's direction as a deep, irreducible feature of the world. It implies that at the fundamental level where fields and particles obey compact equations, the idea of before and after is more flexible than your daily experience suggests. Only when you move upward to systems with many interacting pieces, and especially when you let them exchange energy and information with their environment, does the sharp asymmetry appear. Here, Feynman's way of putting things becomes very simple. He says, in effect, that the distinction between past and future is not written into the underlying dynamical rules. Those rules are, for the most part, time reversal symmetric. The difference emerges when you consider the statistics of enormous numbers of particles and the special conditions under which they start. The one-way character of broken glasses and cooling coffee is not a new kind of force. It is a statement about what is typical when countless microscopic degrees of freedom are allowed to explore their possibilities. From this vantage point, the question about the past becomes sharper. If the laws do not insist on a temporal arrow, yet our world has a very clear one. Something about the large-scale state of matter and radiation must be responsible. The next step is to descend into the crowded world of molecules and collisions, where probability takes over from certainty and the arrow of time shows up as a statistical habit rather than a command. The crowded world of molecules does not live only in laboratories or equations. It is already working in every small accident that leaves a trace, and in every quiet change that you describe with the simple phrase, "too late." Imagine a glass at the edge of a kitchen counter. A sleeve catches it, or a hand misjudges the distance. The glass tilts, hesitates for less than a heartbeat, then falls. While it is in the air, nothing decisive has happened. Momentum and gravity determine a smooth path. When it strikes the floor, The story changes character. In a very short interval, the smooth object becomes a collection of fragments spread over tiles, each with its own path, each transferring energy into sound, heat, tiny vibrations in the material beneath. If you had an unimaginably fine camera, able to resolve the positions and velocities of every atom in the glass, the air, and the floor, you would see an enormous choreography. Bonds stretch, snap, and rearrange. Surfaces that were once buried inside the glass become exposed. Microscopic cracks that existed long before the fall guide the lines along which the material fails. The shattering is not random in the sense of having no cause. It is the detailed, lawful unfolding of a state that has many ways to become more complicated and very few ways to stay simple. Feynman liked to point out that, at the level of those individual atoms, the same reversibility discussed earlier still holds. In principle, there exists a sequence of collisions that would take all of the fragments, send them flying back together along just the right paths, and rebuild the glass. There also exists a pattern of motion of the air and the floor that would withdraw the dissipated energy and funnel it back into the right bonds. The laws do not forbid that precise reversal. What makes it effectively impossible is not a rule, but arithmetic. There are many more ways for the atoms to end up in messy arrangements than in neat ones. A whole glass on a counter corresponds to a very small collection of microscopic configurations. A shattered glass on the floor, with fragments scattered and tilted in countless ways, corresponds to an astronomically larger collection. If you choose among all possibilities without bias, you will nearly always land in the large set, not the tiny one. The same logic applies whether the object is a cup, a bookshelf, or the thin layer of atmosphere over an ocean. You can see the effect in a gentler example Feynman liked, a drop of ink falling into water. At the beginning, the dye is concentrated. It forms tendrils as it sinks and is pulled by currents. The more the liquid stirs, the more the colored filaments stretch, fold, and rethread through the clear water. After some time, the ink is no longer visible as a distinct shape. The entire volume has a uniform tint. At every stage, the molecules follow reversible rules. But once the ink has dispersed, the number of microscopic configurations compatible with evenly mixed is so large that it is overwhelmingly likely to persist. Now recall the early cinema trick with the demolishing wall. When the film is run forward, workers swing hammers, stones fall outward, dust billows, and the structure collapses into a pile. When the film is run backward, dust is pulled inward, stones leap up and settle into a precise pattern, and the finished wall stands where the rubble had been. Audiences in the late 19th century did not require an explanation. They knew from their own lives that bricks do not spontaneously jump into place. Their laughter was already a verdict about probability. The forward sequence looks like a typical outcome of many small perturbations. The reverse sequence looks like a single, exceptional path picked out from an enormous haystack. This way of speaking suggests a distinction that mattered deeply to Feynman. When people say that some evolution is irreversible, they do not mean that the equations only work in one direction. They mean that, given the way many particles explore their possibilities, the odds of returning to a low disorder state are so vanishingly small that you never expect to see it happen unassisted. The phrase "cannot unbreak a glass" is a shorthand for the specific reverse path occupies an absurdly tiny fraction of the available phase space. The person who first turned these intuitions into a concrete framework was Ludwig Boltzmann. He imagined a gas as a large collection of molecules, each moving in straight lines until it collides and changes direction. He then asked how many microscopic arrangements of positions and speeds correspond to a single macroscopic description, like uniform pressure and temperature in a box. For a given macroscopic condition, there is some huge count of microscopic possibilities. Boltzmann proposed that what people call entropy is, in essence, a measure of how many microstates belong to the macrostate. Higher entropy means more ways to realize the same coarse description. In that language, the arrow of time emerges because systems prepared in special, low-entropy states will, under the reversible dynamics, wander into macrostates that have more underlying realizations. They go from rare configurations to common ones. Once there, they almost never spontaneously wander back. A gas that starts confined in one half of a box will, when the partition is removed, spread to fill the whole container. That is not because it prefers one side over the other, but because there are many more microstates in which particles occupy both halves than microstates in which they all sit in one. Everyday life provides endless versions of this pattern. A tidy desk, with papers stacked, pens aligned, and devices in fixed spots, corresponds to a comparatively small region in the space of all possible arrangements. Each time you use the desk, you move an item slightly, leave a page at an angle, or drop a receipt. Over days and weeks, these small changes accumulate. The set of possible configurations consistent with the phrase "desk in a bit of disarray" is vastly larger. Without deliberate effort to push the system back toward the smaller region, it drifts and stays in the larger one. The key point is that nothing in this story introduces a new force pushing toward disorder. The same basic interactions act at all times. The apparent one-way behavior arises from counting and from initial conditions. Systems begin in comparatively constrained states because someone or something has arranged them that way. Heat is pumped out of a refrigerator so that its interior air can remain cold and ordered while entropy is exported to the room. A person chooses to stack books by height, aligning many microscopic details at once. Once that organizing input stops, the natural dynamics takes over, and the system moves into regions of its state space that occupy more volume. Not everyone accepted this view immediately. Joseph Loschmidt, a contemporary critic, pointed out that if the microscopic dynamics is reversible, then any sequence of evolving configurations must have a counterpart in which all velocities are reversed at some moment, leading the system back toward its starting point. From that fact, he argued that entropy could not be strictly increasing. For every path that leads from order to disorder, there is a mirror path that leads back. The resolution lies again in probability. It is true that such mirror paths exist in the space of mathematical possibilities, but there is no natural process that singles them out. To see a Loschmidt reversal in the wild, you would need some mechanism that, at one instant, flips the motion of every particle in exactly the right way. In a gas with astronomical numbers of molecules, or in a glass interacting with a floor and with the air and with thermal radiation, the chance of this happening by chance is effectively zero. The dynamical rules do not forbid it. The statistics makes it irrelevant. This perspective also reframes what impossible usually means in thermodynamics. When you say that all the air molecules in a room will never spontaneously crowd into one corner, you are not asserting a logical prohibition. You are asserting that the set of microstates in which such clustering occurs is so small, compared with the set of microstates in which the gas is roughly uniform, that the expected waiting time for such a fluctuation is longer than the age of the observable universe by a factor that itself is hard to describe without resorting to exponential towers. For any practical purpose, that is indistinguishable from impossible. It is worth noticing how this logic scales. In a small system, with only a handful of degrees of freedom, entropy can fluctuate noticeably. In a nanoscale device, or a cluster of molecules, you can watch energy flow briefly backward, or see a structure that formed earlier dissolve and then reform by chance. These are the rare paths made visible by the limited number of options. In a kitchen, a city, or a galaxy, the number of interacting constituents is so enormous that the rare paths are buried beyond reach. From this vantage point, irreversibility in everyday life is not an extra postulate layered on top of fundamental physics. It is what happens when countless reversible microscopic processes are allowed to run inside a universe that, for reasons still not fully understood, began in a highly ordered state. The broken cup, the cooling coffee, the fading tracks in snow, all of them are small expressions of that underlying statistical drift from constraint to freedom. There is one more twist that Feynman liked to emphasize. Each day, people themselves create low entropy pockets. They close doors and windows to separate indoor air from outdoor air. They align bits on memory chips into patterns that encode photographs and words. They gather scattered thoughts into plans and schedules. In doing so, they export entropy elsewhere, usually as heat or chemical waste. Every act of arranging pushes some subsystem back toward order at the cost of increasing disorder in the wider surroundings. In that sense, everyone is both a passenger and a small engine moving along the same global arrow. You live inside a world where disordered configurations are overwhelmingly more numerous, yet you constantly carve out temporary islands of structure. A clean room, an organized file, a reliable routine. None of these islands can last indefinitely. They are always eroded at the edges by diffusion, friction, and wear. But while they exist, they are evidence of a deeper fact. The arrow of time is statistical, not absolute. It can be locally resisted, at a cost, for a while. The next step is to ask how this picture connects to the idea of records and memory. If irreversibility is about systems rolling into larger sets of possibilities, then any reliable trace of a past event must be a particular kind of structure in that flow, one that remains recognizable even as microscopic details are washed away. That question leads from broken cups and messy rooms to fossils, cosmic background radiation, and the neurobiology of recollection. A world that drifts from tidy patterns into sprawling complexity can feel abstract when you talk about molecules. It becomes clearer when you imagine something simple on the floor of an ordinary room. Suppose you leave a group of children alone with a box of colored bricks. You walk out, close the door, and come back a few hours later. Without seeing inside, your intuition already knows the likely outcome. The room will not be neater. The bricks will not be sorted by color and size and arranged in perfect towers. Pieces will be scattered under chairs, half-built shapes will lie abandoned, and maybe one carefully made structure will still be standing. That easy expectation is already a first encounter with entropy. Ludwig Boltzmann's achievement was to take that kind of everyday intuition and give it a precise backbone. He imagined a simple gas in a box. Instead of treating it as a smooth fog with a single temperature and pressure, he thought of it as an enormous crowd of tiny particles, each flying in some direction with some speed. In that picture, one detailed assignment of positions and velocities to all particles is a microscopic state. What we measure in the lab, however, are things like the pressure on the wall or the overall temperature. Those coarse quantities are macroscopic states. Each macroscopic state corresponds to many microscopic possibilities. A gas that is evenly spread through the box can be realized in an astonishing number of microscopic ways. You can nudge one particle here, another there. And as long as the overall density and energy stay roughly the same, the macroscopic description does not change. By contrast, a gas that just happens to occupy only one corner of the box, leaving the rest mostly empty, has many fewer supporting configurations. Most assignments of positions do not look like that. They look like something closer to uniform. Boltzmann's idea was to say, the macroscopic state with more underlying microscopic realizations is the one with higher entropy. Higher, here, means that if you choose a microscopic state at random under the relevant constraints, you are far more likely to hit that macrostate. In this sense, entropy is not a mysterious fluid or a dark force. It is a way of counting, a measure of how many detailed arrangements fit under one coarse description. When people say that systems evolve toward higher entropy, they are not claiming that there is a new law pushing them. They are saying that when many particles follow the same reversible dynamics, and you forget most of the microscopic details, the macroscopic features you do keep track of will almost always drift toward those descriptions that can be realized in the greatest number of ways. The box of bricks is a good visual anchor. A very neat arrangement, with every brick stacked and aligned, is a low entropy state. There are not many microscopic patterns that look like that. Move a single piece out of line and the scene already changes. A messy room, on the other hand, can be created in countless ways. You can toss a handful of bricks here, leave a wall half-built there, lose a piece under the rug, and the general impression is still chaotic playroom. As I seen Jones tries to in time. Boltzmann paid a price for pushing this arithmetic view in a 19th century scientific culture that often wanted more direct mechanical pictures. Many of his peers were uncomfortable with the idea that something as central as the direction of time could be explained statistically. Some found the notion of irreversibility emerging from reversible laws almost paradoxical. Criticism and misunderstanding followed him for years. Only long after his death, in the year 1906, did his way of thinking become widely accepted as the natural language of thermal physics. The arrow of recognition in his own life pointed outward from a lonely beginning toward later acclaim. While Boltzmann was refining his picture of gases, James Clerk Maxwell was thinking in a more mischievous mode. In a letter written in the year 1867, and then more carefully in a later essay from the early 1870s, he described a playful thought experiment. Imagine a box divided into two halves, each filled with the same gas at the same temperature. In the partition between them, there is a tiny door controlled by an intelligent being, later nicknamed a demon. This small operator watches individual molecules approach the door. When a particularly fast molecule from the left side comes along, the demon opens the door and lets it pass to the right. When a particularly slow molecule from the right side arrives, the demon lets it slip to the left. After a while, the right side accumulates mostly fast molecules and becomes hotter, while the left side accumulates mostly slow ones and becomes cooler. It seems as though the temperature difference has been created without expending energy, and the entropy of the gas as a whole has decreased. Maxwell introduced this demon not to endorse the idea of magic agents in machines, but to probe the foundations of the second law of thermodynamics, the rule that entropy in an isolated system tends not to decrease. If a tiny, clever sorter can lower entropy by using information about individual particles, then the second law must be more subtle than a blanket prohibition. For decades, physicists and philosophers worried over this creature, trying to locate exactly where the bookkeeping of energy and information had been cheated. A more modern understanding turns the story around. The demon is not really outside the laws, it is another physical system. To decide when to open the door, it has to measure the speed of molecules. To keep track of past measurements, it must store information somewhere, perhaps in a memory register. To keep operating reliably, it must eventually erase or overwrite that memory. Each of these steps involves physical processes, and when they are analyzed, the entropy balance is restored. The decrease in entropy in the gas is compensated by an increase in entropy associated with the demon's memory and with the environment that absorbs the heat of its computation. Seen this way, Maxwell's demon becomes an early exploration of how information processing and thermodynamics are entangled. It reminds you that knowing microscopic details and acting on them locally can create pockets of order, but never for free. Somewhere off-stage, entropy is paid, whether in the warmth coming off a computer chip or in the biochemical waste of a living organism that sorts its environment. Feynman had a soft spot for such paradoxes because they force a clear separation between different levels of description. The demon story tells you that if you imagine an all-seeing agent with unlimited control over microstates, you can temporarily bend the arrow of time in a subregion. But once you account for the agent as part of the physical world, obeying the same rules, the global arrow remains. No actual arrangement of gears, atoms, and circuits escapes the larger statistics. This is the same point that appears when you think about the earlier spin-echo experiments. In that context, a carefully designed sequence of pulses plays the role of the demon. It manipulates the microstate in a very specific way, temporarily steering it along an unlikely path that makes a decaying pattern reappear. Yet the creation of this cunning control requires external apparatus, energy input, and often an increase of entropy elsewhere. You do not break the second law. You exploit the fact that it is about totals, not about small regions in isolation. In the late 20th century and the early years of the 21st, this statistical picture received further support from detailed work on very small systems. Researchers began to trap single colloidal particles in optical tweezers, stretch individual molecules of biological polymers, and drive nanoscale devices back and forth between configurations. Because these systems involve relatively few degrees of freedom, And because the experiments could be repeated many times under carefully controlled conditions, it became possible to measure not just average behavior, but the whole distribution of outcomes. Out of this work came what are now called fluctuation theorems. They relate the probability of observing a certain amount of entropy production in a given driving process to the probability of observing the opposite sign. In simple terms, they say, in small systems, over short times, there is a non-zero chance of seeing entropy decrease, but that chance falls off in a precise way as the magnitude of the decrease grows. The second law, which says that entropy tends to increase, emerges as a statement about averages over many trials or about long timescales. Not as an absolute ban on every negative fluctuation, these results did not undermine Boltzmann's view. They refined it. They show that the march toward disorder is a statistical law that allows for rare exceptions in small arenas. Over the long run, and especially when many particles are involved, the positive direction dominates so overwhelmingly that the negative fluctuations become irrelevant. For a dust, grain, or a protein, you might catch a brief roll uphill. For a cup of coffee, a human body, or a star, the downhill tendency is effectively total. Feynman liked to say that the interesting physics lives in such statistical regularities rather than in the exceptional cases. The microdynamics cares little about time direction. The macro behavior, once you fold in probability, cares very much. The arrow you feel in your bones is the emerging pattern of immense numbers of degrees of freedom flowing from states that occupy small regions of their possible configuration space to states that occupy vastly larger ones. Thinking this way also changes how you interpret common words. When you say that a system relaxes to equilibrium, you are not naming a special resting place ordained by a law. You are saying that the system has moved into the region of its macroscopic description that corresponds to the largest number of microscopic arrangements, and that, once there, it is unlikely ever to find its way back into the narrow corridors of low entropy. When you say that disorder increases, you should be cautious. Disorder in ordinary language suggests meaningless mess. In the Boltzmann sense, it is more precise to say that the system has moved to a state in which your chosen coarse variables lose track of more and more detailed correlations. The ink in water becomes uniform not because the molecules care about being messy, but because the number of ways for them to be thoroughly intermingled is so much greater than the number of ways to remain segregated. Seen through this lens, entropy is also about ignorance. Not ignorance in a moral sense, but in a structural one. A low entropy state is one where extensive knowledge about microscopic details is encoded in a few macroscopic observables. A deck of cards in perfect order carries more specific information than a deck that has been thoroughly shuffled, even though both are produced by permutations of the same underlying elements. Once you shuffle enough, knowing that you hold 52 cards tells you almost nothing about the particular sequence. The entropy of the shuffled deck is higher because the same macroscopic description corresponds to many more microscopic possibilities. This idea connects back quietly to memory and records. A photograph, a fossil, a crystallized pattern in a rock are all low entropy structures at some scale. They pick out a tiny subset of available configurations to encode something about a past event. Creating and preserving them requires work and a suitable environment. Left alone in a hotter, more chaotic surrounding, they would blur and eventually lose their specificity. That slow erosion is another face of the same statistical drift that scatters bricks and shatters glasses. For Feynman, the attraction of Boltzmann's perspective was that it allowed him to say where the difference between past and future really sits. It is not inside the elementary laws, which are nearly all reversible. It is in the way great crowds of particles explore their possibilities, given the particular constraints with which the universe seems to have begun. The arrow of time is the name we give to the direction in which entropy increases, which is the direction from rare, highly constrained macrostates toward overwhelmingly typical ones. This is why repeated appeals to some additional force of disorder are misleading. There is no special hand pushing coffee to cool, rooms to become untidy, or batteries to run down. There is only the fact that, For systems with many components, the vast majority of microscopic states look like what we call disordered. Given a chance to move freely, systems will almost certainly fall into those states and stay there. You can resist this drift locally. You can clean the room, refrigerate the food, compress the gas, or sort the cards. But in each case, you do so by increasing entropy somewhere else, usually by dumping heat into an environment or consuming fuel that took entropy-lowering processes elsewhere to create. The global account never comes out ahead. At best, you move structure around. Put this all together, and the earlier question about why the past feels different from the future gains a sharper shape. The past is the direction in which, if you could look, you would see lower entropy states, greater constraints, more correlations that have not yet been washed away. The future is the direction in which those correlations have been diluted, folded into broader statistical patterns. The difference is not that the laws change sign at some invisible boundary, but that the phase space volume associated with different macrostates is wildly uneven. In that sense, the universe does not shove anyone toward tomorrow by decree. It does not carry a metaphysical arrow nailed into its fabric. It simply presents far more ways to be spread out than to be neatly arranged. Given that imbalance, every unforced motion tends to drift along the same gradient. The world does not push us toward the future with a mysterious hand. It simply has far more ways to be disordered than to be ordered, and we are carried along by that current of probability. The current that carries the world from order into disorder does not slide past cleanly. It scuffs and scratches and imprints as it goes. That is what we call memory. Think of a very small scene. A faded photograph in a drawer. A movie ticket tucked between pages of a book. A message still stored on a phone that has long since fallen out of daily use. None of these objects is the moment itself. The conversation has ended. The film is over. The person in the photograph has changed. Yet each object is shaped by an event that no longer exists in the present tense. And somehow that shaping lets the event continue to matter. In the language of entropy, a record is a physical system whose state has been changed in a way that depends on something that happened earlier. Light from a scene hits photographic film and alters molecules in a pattern that correlates with the arrangement of faces and shadows at that time. Charges in a memory chip are moved into a particular configuration that can later be read as letters, numbers, or pixels. Networks of neurons in a brain adjust the strength of their connections after an episode of experience. In every case, the creation of the record involves energy flow and dissipation. Heat leaks into the surroundings. Entropy increases somewhere. That cost is not incidental. It is part of the reason why records are directional. You do not usually find a stone whose internal crystal structure rearranges itself to encode an event that will happen tomorrow. You do find stones whose structure has already been changed by stress, heat, and chemistry associated with events that happened long ago. The arrow of time in memory is just the arrow of increased entropy seen from a particular angle. Once you start looking, the world is full of long-term records that nobody intended to make. Fossils are one obvious kind. A living creature dies. Its soft tissues decay. Minerals seep into whatever remains. Over spans of time that make human calendars look trivial. The surrounding rock hardens and moves. In the end, you get a preserved shape, sometimes very detailed, that encodes something about the anatomy and even the behavior of an organism that no longer exists. Sedimentary layers tell similar stories for climate and geology. Each thin band in a cliff face represents a period when materials settled, compressed, and changed. Grain size, chemical composition, and trapped microfossils all carry information about temperature, sea level, and biological activity at the time they formed. Ice cores from Greenland and Antarctica are another form of archive. Year after year, snow falls, compacts, and traps bubbles of ancient air. By drilling down and measuring the composition of those bubbles, people can reconstruct atmospheric conditions and temperature trends stretching back hundreds of thousands of years. In all of these cases, the possibility of reading the past depends on the world having been ordered enough and quiet enough in certain respects for patterns to persist. If the crust had churned more violently, or if chemical reactions had blurred every structure faster than they could be buried, there would be fewer fossils and less readable rock. If snow layers had mixed thoroughly every season, or if ice had flowed too erratically, the detailed stripes of climate history in the cores would be washed out. Memory, even at this planetary scale, depends on a certain restraint in the rate of microscopic scrambling. Among the most striking physical records is one that fills the entire sky. In the middle of the 1960s, Arno Penzias and Robert Wilson were working at Bell Laboratories with a large radio antenna, trying to track sources of noise that were interfering with their measurements. They kept encountering a persistent hiss, the same in every direction, that did not go away even when they cleaned the equipment and chased down local sources. Eventually, in conversation with cosmologists, they realized that what they had found was not a flaw but a signal. Faint microwave radiation coming from all over the cosmos. That discovery, in the year 1965, was later understood as light left over from an early phase of the universe, when it was hot, dense, and filled with a plasma of electrons and nuclei. As the universe expanded and cooled, there came a time when atoms could form and radiation could travel freely. The microwaves that Penzias and Wilson detected are those photons, stretched in wavelength by expansion, still flying through space. They form a kind of baby picture of the universe from when it was only a few 100,000 years old. This cosmic microwave background is an example of memory at the largest scale we know. Tiny variations in its temperature across the sky encode information about the distribution of matter and energy at that early time. Later structures, like galaxies and clusters, grew out of those initial ripples. By measuring the pattern carefully, physicists can infer details about the composition and geometry of the universe and about its subsequent expansion history. Here again, the possibility of reading the record depends on the fact that entropy has increased since then. The early universe was in a very special, low-entropy state, simple enough that small deviations from uniformity could survive and be traced. Feynman's way of summarizing this is simple. We can reconstruct the past, whether it is the path of a thrown ball a second ago or the evolution of galaxies over billions of years, because the present contains reliable traces that have not yet been completely scrambled. Those traces exist because entropy has been rising from a lower baseline. If the universe had always been in a near maximal entropy condition, with matter and radiation as mixed as possible, there would be no stable structures to serve as records, and no contrast from which to infer earlier states. This connection between memory and entropy is clearest in the brain. What you call remembering is not a passive replay. It is an active process in which patterns of activity and connectivity in neural circuits change over time. When a new experience is encoded, synapses are strengthened or weakened. New proteins are synthesized. Electrical and chemical environments shift. All of this takes metabolic energy. The brain is one of the most energy-demanding organs in the body. The entropy generated by those biochemical processes is exported as heat and molecular waste. From a physical point of view, a memory is a relatively low entropy configuration of some subset of neural tissue, a pattern that could easily be disrupted if the underlying components were allowed to wander freely in their space of possibilities. The body pays a continuous cost to maintain those patterns within a certain range, just as a computer pays a cost in power to preserve bits in a device. The psychological arrow of time, the fact that you remember yesterday but not tomorrow, is tied to the thermodynamic arrow. It is rooted in the fact that we build and maintain records in one temporal direction by burning fuel and increasing entropy in the surroundings. A stark way to see this is to consider what happens when the recording machinery is damaged. The film Memento, released in the year 2000, follows a character who cannot form new long-term memories. He relies on photographs and notes and tattoos to navigate his life. The physical events in his world continue to follow the same causal chains as always. Objects move, people act, consequences unfold. But his personal past, as a coherent narrative, is always collapsing. Without a functioning system for creating and storing traces, the subjective sense of time fragments. Even though the underlying physics has not changed, there is a quieter version of the same theme in ordinary forgetting. Most of what happens during a day leaves no durable impression. The precise pattern of leaves on a tree you passed, the sequence of small noises in a cafe, the variations in tone in a stranger's voice, all involve complex microstates. They influence you briefly and then are gone from conscious recall. Yet physically, they did not vanish. The air vibrated, molecules collided. A cascade of neural firings took place. Those microstates have joined the vast, undifferentiated sea of higher entropy configurations. This leads to a natural question. If, at the fundamental level, information about every interaction is carried forward in correlations among particles and fields, why do we remember so little? Why can we not, for example, call back the exact pattern of photons that hit our eyes on a given morning? The answer is that many microscopic configurations map onto the same macroscopic appearance. When you look at a photograph, you do not see the precise arrangement of all the atoms in the paper or the digital file. You see shapes and colors arranged into recognizable forms. Your visual system and your memory strip away detail and keep structure. The same is true for fossils and rock layers and ice cores. They encode some aspects of the past at the expense of countless others. In statistical terms, a memory is a macrostate that aggregates many possible microstates into one functional category. Every time microscopic noise perturbs the underlying details without breaking the larger pattern, entropy increases while the effective record persists. Eventually, accumulated noise can cross thresholds that do matter, and the pattern fails. Photographs fade, ink smears, neural connections weaken. The memory is lost, not because the universe has erased its past, but because the particular low-entropy structure that made that past accessible has finally been overwhelmed. Feynman sometimes described the world as a kind of grand bookkeeping system, in which nothing is ever truly forgotten, only dispersed. The full microscopic description of the universe at any present time contains, in principle, enough information to reconstruct earlier states by running the equations backward. In practice, that reconstruction would require control over degrees of freedom so enormous and fine-grained that no physical agent could achieve it. The records that humans and their instruments actually use are sparse and coarse. They encode just enough to be useful for prediction and orientation, and no more. You can picture the situation with a simple image. Imagine an empty room in which dust gradually settles. Every time someone walks through, a subtle swirl is created. Every time a window is opened, currents reshape the patterns. Over many such disturbances, the dust grains come to occupy positions that depend on the full history of motions and breezes. In a strict sense, the final arrangement contains a record of everything that ever happened inside the room. Yet, when you enter and look around, you cannot read that record. The patterns are too delicate, the correlations too spread out over too many particles. Your eyes and hands, and even your best microscopes, are coarse instruments. They are tuned to larger-scale structures like footprints or scratches on furniture, not to the invisible choreography of specks in air and on surfaces. The information is there, but it is not in a form that any realistic observer could extract. On the scale of the cosmos, matter and radiation are the dust. Every interaction slightly reshapes fields and trajectories. Each emission of light, each collision, each chemical reaction leaves some microscopic influence on the later state. Taken together over cosmic time, these influences encode a staggering amount of detail, but only certain robust arrangements stand out enough to count as records we can actually use. The background radiation, the distribution of galaxies, the atoms in rocks and bones, the synapses in living brains. So, when you hold an old ticket or open a file of photographs, you are interacting with one of these rare, durable configurations. It is a small, privileged island in a sea of possibilities, maintained against the background drift by the same processes that create and preserve order. Its existence is possible at all only because the universe began in an extraordinarily low entropy condition that allowed such islands to form and persist before they dissolved. The past, in that sense, has not gone anywhere. It is woven through the present in layers of correlation and structure, most of them far beyond our ability to disentangle What we call remembering is a narrow form of access to a few of those layers, filtered through limited senses and limited brains. The real mystery, once you accept that, is not why memories fade, but why records ever exist in the first place. If every reliable trace depends on entropy rising from an exceptionally low starting point, then understanding why there is any room for memory at all means asking why the entropy was so low to begin with. When you ask why there is any room for memory at all, you end up being drawn back to the very first scenes of the cosmic film. Not to the middle chapters where stars form and galaxies collide, but to the opening minutes when everything was hot, dense, and strangely simple. If the universe were a movie, those opening frames would look almost dull at first glance. A glowing fog of radiation and particles, nearly the same in every direction. No stars, no planets, no dark silhouettes of galaxies against the sky. Yet that plainness is exactly what causes arguments. Why did the story begin in such an improbably tidy way? The strongest visual clue we have about that early state is the cosmic microwave background. In the year 1965, Arno Penzias and Robert Wilson pointed a radio antenna at the sky and found a soft hiss that came from every direction they tried. The noise did not vanish when they cleaned the equipment. It did not depend on the time of day or the season. Gradually, it became clear that they had stumbled onto relic light from the young universe itself. Later missions mapped this background in detail. The result is a kind of baby picture of the cosmos. It shows a sphere around us, glowing at a temperature just a bit above absolute zero, almost perfectly uniform, with only tiny mottlings where the temperature differs by a few parts in 100,000. Those mottlings are crucial because they seeded later structures, but the overwhelming impression is sameness. From the point of view of entropy, that sameness is odd. In ordinary thermodynamics, a smooth, evenly filled box of gas is a high-entropy state, compared with one in which the gas is crammed into a corner. When gravity is important, though, the roles change. A nearly uniform distribution of matter on cosmic scales is actually very special. Given time, gravity tends to make matter clump. Smoothness is unstable. Left to itself, a cloud collapses into stars, and stars fall together into galaxies and clusters. Roger Penrose emphasized this difference. In the late 1970s, he proposed what he called the Weyl curvature hypothesis. The technical details live in the geometry of space-time, but the intuitive content is simple enough to state. There are different ways that space-time can be curved. Some pieces of curvature are directly tied to how much matter and energy are present. Another piece, called the Weyl part, captures the tidal, lumpy, wave-like aspects of gravity, the distortions that give rise to structures like black holes and gravitational waves. Penrose suggested that near the initial state we call the Big Bang, this lumpy piece of curvature was essentially absent. In other words, the gravitational field was as smooth as it could reasonably be, even though the overall density was enormous. That kind of configuration corresponds to extremely low gravitational entropy. As the universe expands and inhomogeneities grow, the Weyl curvature increases and gravitational entropy rises. The arrow of time we experience in this picture is tied to the growth of this particular kind of irregularity. A more homely way to say this is that the early universe was like a freshly cleaned house with almost no dust and no clutter. The surfaces were bare, the shelves empty. Gravity provides the means by which dust can gather, clumps can form, and complicated messes can develop. But at the beginning, that capability had not yet been used. Everything was laid out evenly, ready for structure to form. From that starting point, entropy had a huge amount of room to grow. This is exactly the kind of story Feynman had in mind when he told his students that the arrow of time depends not only on the laws, but also on the boundary conditions. The dynamical rules, taken by themselves, are almost blind to direction. What breaks the symmetry is the fact that the universe appears to have started in a very special, low entropy state. Without that, ink would already be mixed, coffee already lukewarm, and the space available for making new records would be far smaller. You can borrow a metaphor from literature. Imagine a very long novel. At the start, the author introduces only a handful of characters and a single quiet location. The relationships are simple. The conflicts are just suggestions. This sparse beginning gives enormous freedom for the later chapters to branch, complicate, and intertwine. If the book began instead with every character already entangled with every other in a crowded web of unresolved business, there would be less room for development. The past omnipresence of conflict would leave fewer directions to expand. In our universe, the first chapters are sparse in a similar way. Energy and matter are present in vast amounts, but the patterns they form are restricted. The cosmic microwave background tells us that at the time when atoms first became stable and light could travel freely, the differences in density from place to place were tiny. The gravitational field had not yet evolved complex structures. That is the stage onto which all later drama enters. Modern cosmology gives this special starting point a name: the past hypothesis. It is the assumption that, at one temporal boundary, the universe occupied a state of remarkably low entropy compared with the generic possibilities. From that single asymmetrical condition, the statistical arrow of time follows. Entropy increases away from that boundary, and records, memories, and irreversible processes become possible. Why should such a hypothesis be needed at all? Because the laws by themselves do not single out any particular macro state as the beginning. If you wrote down all the microscopic configurations consistent with a given energy and volume and chose one at random, it would almost never be as smooth and simple as the early universe appears to have been. It would be more like a later, well-mixed state, with matter clumped into black holes and radiation scattered without obvious structure. To explain why our actual history includes a long era of rising entropy, you have to start from an unusually low value. Different theories of the very early universe can be understood as attempts to explain or at least embed this past hypothesis. Inflationary models propose that shortly after the Big Bang, space itself expanded at an enormous, accelerating rate for a brief period. This rapid stretching smooths out irregularities and drives the observable region toward uniformity. Tiny quantum fluctuations present before or during inflation, then get magnified into the small ripples we see in the microwave background. The end result is a universe that is both very smooth on large scales and slightly mottled in just the right way to grow galaxies later. Inflation, if correct, makes the uniformity of the cosmic microwave background less surprising. It offers a dynamical reason why our region looks so even. But it does not completely dissolve the puzzle. The conditions needed to start inflation, and to end it in a way that leads to a universe like ours, are themselves special in the space of possibilities. You can say that inflation explains some aspects of the low entropy beginning in terms of earlier structure, but unless inflation happens under almost arbitrary circumstances, you have only pushed the question back. Other ideas explore different directions. Cyclic cosmologies suggest that the universe undergoes repeated phases of expansion and contraction, or bounces from one aeon to another. In such pictures, our Big Bang is not the absolute beginning, but a transition. The challenge, then, is to show how a low-entropy starting point can recur without violating the trend of entropy growth across cycles. Penrose himself has proposed a version called conformal cyclic cosmology, in which the remote future of one aeon, emptied of mass and scale but filled with radiation, can be reinterpreted as the smooth, low-entropy beginning of the next. Multiverse scenarios imagine a larger structure in which many regions, like our observable universe, perhaps with different physical constants or laws, bud off from a common background. In that setting, our low-entropy initial state might be one branch among many. The question becomes a statistical one. Under what circumstances do observers like us typically find themselves, and is a smooth beginning a generic feature or a rare accident? Here, too, the answers are not settled. What matters for our thread is not which of these speculative frameworks, if any, will survive. It is that all of them must confront the same basic fact. The universe we see around us, with its clear arrow of time and its abundance of stable records, appears to have arisen from a configuration that was extraordinarily special in entropy terms. That specialness is encoded in the uniformity of the cosmic microwave background, in the relative scarcity of black holes at early times, and in the very existence of large-scale structure that formed gradually rather than being present from the start. Feynman's temperament leaned toward frankness about such gaps. He was happy to say, when necessary, that physicists simply do not yet know why the boundary conditions are what they are. He did not regard this admission as a flaw in the whole enterprise. For him, it was part of scientific honesty, distinguishing clearly between what the equations describe well and what remains imposed from outside as an input. From this perspective, the universe gives us an arrow of time as a kind of gift. It hands us a cosmos in which entropy has room to grow, where local pockets of order can form and persist for long stretches before dissolving, and where information about earlier states can be stored in durable patterns. The price of that gift is the mystery of the initial condition. We do not yet have a fully convincing story about why the opening frames look the way they do. Realizing how much depends on that opening has an odd effect on the question of the past. It shifts attention away from what happened before the Big Bang toward what structure made the Big Bang such a good starting point for stories. Every memory, every fossil, every page of history relies on the long slope of entropy increase from that low plateau. If the beginning had been more chaotic in the gravitational sense, or if entropy had already been near its maximum, there would have been little room for complexity to develop and persist. You can think of your own life against that background. The fact that you can sit in a room, keep a notebook, and reflect on decades of personal and cosmic history is not just a matter of local biology. It is linked, through long chains of cause and effect, to the surprisingly simple state encoded in the microwave background. The arrow of time that runs through your memories is an extension of the arrow that runs from that first smooth fireball through star formation and chemical evolution to the present. By the end of this line of thought, the original question, does the past ever truly disappear, has been sharpened rather than resolved. On the one hand, the underlying laws do not seem to delete information. They evolve states into states in a way that, in principle, preserves correlations. On the other hand, the forms of memory that matter to finite beings like us depend on special low-entropy structures that can be created and maintained only because of the universe's peculiar beginning. If the past has never gone anywhere, in the sense that it remains woven into the current state of the cosmos, then the apparent one-way loss we experience is about our limited and costly ways of making records. Those records are islands carved out of a sea that is always rising. Their very possibility comes from the fact that the sea started low. So the puzzle left hanging at this point is less about metaphysical origins and more about responsibility. If we live in a universe where the past is encoded in everything, and where the future will inherit the consequences of our actions in equally physical ways, then the low-entropy beginning is not only a scientific curiosity, it is the backdrop against which meaning and accountability exist. If the past never truly goes away and is instead the unfolding of a very special start, what, exactly, do we owe to the future states that will have to live with the traces we are leaving in this ever-increasing entropy? If the universe began in a way that leaves room for many possible stories, then Feynman's next move is to ask how those stories are actually assembled. Not just which events happen, but how nature chooses a path from one moment to another. On a blackboard, his answer looks almost like a child's doodle. He draws 2 points, A and B, far apart. Then, between them, he begins to sketch squiggly lines. One line goes straight, more or less the path you would expect from a classical particle. Another meanders, looping and coming back on itself. A third takes a wild detour, rising high and then swooping down. In the space between A and B, the chalk becomes a dense tangle of possible trajectories. In ordinary, pre-quantum thinking, only one of these paths is real. A particle has a definite position at each time and moves along a single track, perhaps influenced by forces, but always with one history. Feynman's quantum view is more radical. He asks you to imagine that, at the microscopic level, the particle does not choose a single route. Instead, it somehow explores all of them. Every admissible path from A to B contributes to the final outcome. What we call the observed result is a kind of weighted sum of all those possibilities. The technical implementation of this idea is elaborate, but the core picture is vivid and simple. For each fanciful trail connecting the starting and ending points, there is a kind of phase tag, an oscillatory factor. When you add their effects together, some sets of paths reinforce one another while others cancel. The classical path, the one we would have expected from older physics, is not singled out by decree. It emerges as the route where the contributions from neighboring possibilities line up constructively. This way of thinking is called the sum over histories. It does not mean that all histories are equally real in a naive sense. Rather, it says that what we observe as a single definite event is the net result of many underlying alternatives interfering with one another. Paths that are wildly different from the classical one tend to cancel out because their phases fluctuate rapidly. Paths that are close to the classical one tend to agree and survive. Now return to the question of the past. When you look at a present situation and ask what must have happened, you are doing something analogous on a larger, fuzzier scale. Consider a glass lying shattered on the floor. There are many conceivable ways for those fragments to have arrived in those positions. The glass could have been knocked by a cat, brushed by a person, shaken off a shelf by an earthquake. Each scenario involves a chain of events, a path in the space of possibilities, connecting some earlier intact state to the current broken one. Your brain does not explicitly sum over all those micro-histories in the quantum sense, but it does sift them. It uses available evidence, the position of the cat, the absence of other disturbances, the timing of sounds to favor some reconstructions over others. The past you settle on is the one that fits every trace you can access. The path consistent with all the records, from obvious ones like footprints to hidden ones like dents in furniture or tension in your own muscles. In Feynman's formalism, the sum over histories is anchored by boundary conditions. You specify where the system begins and where it ends, and the mathematics tells you how to combine all the intermediate routes. The laws themselves remain neutral with respect to time, direction. They simply relate configurations. But choosing a start and finish imposes a narrative frame. You are asking, given that the system was in state A and is later in state B, what is the amplitude for that transition? This subtlety matters. The arrow of time in the sum over histories does not come from the basic rule that assigns phases to paths. That rule is symmetric. The orientation appears when you choose to condition on one set of facts and infer another. In practice, we condition on past preparations and predict future observations, but the formalism itself would be just as happy if you reverse those roles. It is our habit and the thermodynamic asymmetry of our environment that tilt the interpretation. Some films in recent decades play with a similar structure. Arrival, released in the year 2016, uses a story in which linguistic understanding changes the protagonist's relationship to time. Past and future scenes are intercut in a way that suggests a kind of all-at-once perception, where earlier and later moments are parts of a single shape rather than points on a line. Interstellar, which opened in the United States on October 26, 2014, bends its narrative around gravitational time dilation and a climactic scene inside a higher dimensional construct where cause and effect feel rearranged. These movies are not literal illustrations of Feynman's quantum mechanics, but they resonate with one aspect of it: the idea that you can view events not just as a forward progression, but as part of a connected whole, determined by boundary conditions. The question shifts from what comes next to what entire configuration of histories is consistent with what we see. The arrow of time remains, because entropy and memory still flow in one direction, but within that flow, there is room to imagine non-trivial structures of causality. Inside your own nervous system, something like a sum over histories happens whenever you recall or interpret. Sensory input at any moment is messy and partial. The brain receives fragments: a sound here, a shape there, a faint smell, a flicker of emotion. From these, it generates many candidate explanations. Perhaps the rustle in the next room is the wind. Perhaps a pet. Perhaps another person. Neural circuits activate patterns representing each possibility. Through further processing, some patterns are suppressed, while others gain strength, until one coherent narrative wins the competition. That winning narrative becomes what just happened. Later, when you store or retrieve a memory, your brain again evaluates multiple reconstructions. Each recall is not a simple replay, but a new synthesis that must be consistent with everything else you know. Over time, the remembered past can drift as details are filled in or dropped, though it remains tethered to certain robust anchors. Photographs, other people's accounts, physical consequences that cannot be wished away. In that sense, the past is always a choice made under constraints. At the micro level, quantum amplitudes for different histories combine, and the outcome we register is shaped by interference between what could have happened and did not. At the macro level, cognitive systems consider many explanatory paths and settle on those that best match the available evidence and the organism's needs. The physical arrow of time sets the direction in which new traces are laid down. The narrative arrow of time organizes those traces into a story. Feynman's own path-integral approach is grounded in concrete experiments. Double-slit interference for electrons, for example, has a particularly striking interpretation in this language. An electron leaves a source, passes through a region with two openings, and is later found at some point on a screen. Classical thinking would assign it a definite trajectory through one slit or the other. The interference pattern on the detector, however, suggests that the electron behaves as if it has been aware of both openings. In the sum over histories, paths that pass through each slit contribute, and their phases combine to enhance or suppress the probability of arrival at different spots. What makes this remarkable, in our context, is that even the paths you might call unreal, those in which the electron goes through the slit you later block, or loops in peculiar ways, you never directly observe, affect the final statistics. They are not realized in the single run you watch. The detector clicks in one place, not in many, but to compute the odds of that click, you must include contributions from trajectories that did not happen. They leave a mathematical trace in the way they modulate the interference pattern. In more complex systems, similar interference effects arise in superconducting circuits and other mesoscopic devices. Coherent superpositions of different current paths affect measurable quantities like magnetic response and transport. Again, there is a sense in which unrealized options help shape the probabilities of realized outcomes. The world you actually see at the end of an experiment is one branch, but its likelihood was sculpted by the presence of many neighboring branches. This has an almost poetic echo in everyday decisions. When you look back on your own life, you can often list alternate routes you might have taken. Different schools, jobs, relationships, cities. Those paths are not realized, but they haunt the evaluation of the path you did walk. They exist as counterfactual histories in cognitive space. The physical universe did not branch to actualize them as separate worlds, at least in the modest picture we are using here. Yet in imagining them, and in weighing how your present depends on choices among them, you are doing a kind of mental sum over histories. Feynman would likely insist on a clear separation between metaphor and mechanism. Quantum amplitudes are not feelings, but he might also appreciate that minds built from matter obeying quantum laws would naturally evolve ways of handling possibilities, not just actualities. The very fact that you can think it could have gone differently is another layer of structure on top of the deeper fact that, in the universe's fundamental description, many paths are always being considered. All of this feeds back into the notion of the past as reconstructed rather than laid out. The sum over history's framework tells you that the basic equations are symmetric in time, yet they invite you to phrase questions in terms of boundaries. Given that a system was prepared in this way and later observed in that way, what is the amplitude for that pair of conditions? Our human use of physics mirrors this. We prepare experiments, then look at results, and then infer the connecting stories. The direction is fixed not by the law, but by the fact that we have records of preparations and only probabilistic expectations about outcomes. There is a quiet shift here from the picture of a pre-recorded film to one of continual story selection. Instead of imagining a universe with a single, rigidly determined script stretching from the Big Bang to the far future, the sum over histories encourages you to think in terms of constraints and allowed patterns. The opening low-entropy condition is one set of constraints. The present arrangement of matter and radiation, with all its memories and fossils and devices, is another. The actual world line between them is one of many that could have been, but it is one that satisfies both. The arrow of time, in this view, acquires an additional layer. It is not only the direction in which entropy increases, it is also the direction in which stories are fixed. Moving from past to future, new constraints are added. More records, more traces, more entanglement between different parts of the universe. The space of compatible histories narrows as more conditions accumulate. The path we call our history becomes a more sharply defined thread, running through an ever denser web of correlations. When you stand in the present and look backward, you are not seeing a simple replay of what really happened. You are navigating this web, following strands that lead from now to then. Every fossil dug up, every document opened, every childhood scene revisited in thought, further restricts the set of histories consistent with what you know. The past you experience is this continually refined selection, a story edited after the fact to fit all the available data. In Feynman's way of looking, the universe does not simply unfold once and for all. It unfolds, and is also, at every moment, being redescribed by the records it has produced. The physical laws allow many histories. The low entropy beginning and the accumulation of traces select a small subset. Within that subset, conscious beings like us perform yet another layer of selection, choosing narratives that make sense of our limited view. In that sense, the cosmos is not only happening, it is, through us and through its own structures, telling itself what has happened. If the universe is always busy leaving traces of what has happened, a natural rebellious thought appears. Could we ever make it take something back? If we were clever enough, careful enough, could we force a whole physical system to run in reverse and watch entropy fall instead of rise? That is the spirit of a challenge raised in the 19th century by Joseph Loschmidt. He thought seriously about Boltzmann's picture of gases and found a sharp edge in it. Boltzmann had argued that a gas tends to move from less probable macrostates to more probable ones, from special arrangements to typical ones, and that this drift is what people call the second law of thermodynamics. Loschmidt replied with a simple but unsettling observation. Imagine you have a box of gas evolving under the usual microscopic laws. At some particular instant, you somehow reverse every single molecular velocity. Every particle that was moving north now moves south with the same speed, and so on in all directions. If you do this exactly, the subsequent motion will retrace the earlier motion in reverse. Whatever the gas did to approach equilibrium, it now undoes. The quantity Boltzmann used to track entropy, which he called H, will move in the opposite direction. Entropy will seem to decrease. Loschmidt made this point public in the year 1876. It pushed the whole community to look again at what exactly the arrow of time meant. If the laws of motion are reversible, and if there is at least one way to make entropy go down, how can we say that disorder must always increase? Where does the must come from? The modern answer does not deny what Loschmidt said. It accepts that if you could carry out that perfect reversal, you would see entropy run backward for a while. The catch is hidden in the phrase, if you could. For a gas with a number of particles comparable to Avogadro's constant, reversing every velocity exactly is not merely difficult, it is fantastically, practically impossible. It would require a level of control and knowledge over microstates that no physical apparatus, itself made of atoms and subject to noise, can achieve. Still, the idea did not go away. It morphed into a question that experimentalists in the 20th century could try to approximate. Can we find small systems where a kind of time reversal can be engineered, just enough to make the intuition concrete? One of the clearest examples is the phenomenon called spin echo. In the early 1970s, Malcolm Warr, Erwin Rimm, David Pines and their collaborators explored this effect in solids using nuclear magnetic resonance. The basic setting is simple to describe. Take a piece of material in which the nuclei of atoms have spin, behaving like tiny bar magnets. Place it in a strong magnetic field. The spins tend to align with the field, but if you tip them slightly using a short radio frequency pulse, they begin to precess together, like an array of spinning tops. At the beginning, many of these spins point in almost the same direction in the plane perpendicular to the field. Their contributions to the measured signal add coherently, producing a strong response. As time goes on, slight differences in the local environment, small variations in field strength, interactions with neighboring spins cause them to precess at slightly different rates. They fan out around the circle. Their phases drift. The collective signal decays, even though each individual spin continues to precess regularly. From a macroscopic point of view, it looks as though the system is forgetting its initial order. Information about the alignment is being scrambled into microscopic degrees of freedom that the apparatus no longer registers. Entropy, at least in an effective sense, is increasing. Now comes the clever part. After a certain waiting time, the experimenters apply a second radio pulse, designed to flip the spins in a specific way. Spins that were ahead in phase are now placed behind, and those that were behind are put ahead. After this manipulation, the dephasing process continues, but in a kind of mirror image. The spins that had wandered farthest now start to converge. At a particular later time, they realign, and the macroscopic signal suddenly reappears as a sharp pulse. That is the echo. What happened is not magic. The overall evolution is still governed by the same microscopic laws. But the sequence of pulses has played a role somewhat like Loschmidt's ideal reversal, at least for some privileged degrees of freedom. The spins are made to retrace their path in the abstract space of orientations. A pattern that seemed to have dissolved into noise returns. Effects like spin echo show that, with enough insight and control, you can coax a subsystem to behave as though time has run backward for a moment. They are the laboratory shadow of a more grandiose fantasy that sometimes appears in popular culture, the idea of reversing time itself. Christopher Nolan's film Tenet, released in the year 2020, plays on this fantasy. In its world, objects and people can be inverted, experiencing cause and effect in the opposite order from everyone else. A bullet flies from a wall back into a gun. An explosion refolds into a pristine building. Characters who are inverted move through a landscape where others are going forward, leading to intricate sequences where the same events are seen from incompatible temporal perspectives. The physics in the film is not meant to be a literal model of real-time reversal, but it taps into the same intuition that Loschmidt voiced and that spin echo exploits. If the laws at their core do not care about forward versus backward, perhaps there is a way, with sufficient technology, to flip the arrow in some region and watch things unhappen. Here, Feynman's sober instincts are useful. He would ask first what exactly is being reversed. In spin echo, only certain aspects of the spin system are returned to a previous configuration, and only for a finite time. The rest of the universe marches on. Heat is produced in the circuitry that generates the pulses. Entropy is dumped into the environment. Globally, the second law is not violated. A local order has been sharpened at the expense of greater disorder elsewhere. The same would hold for any realistic attempt to implement a more dramatic reversal. To reverse a complex system, you must record intricate details about its state, compute how to invert them, and then apply a coordinated intervention. Each of those steps has a thermodynamic cost. Measuring creates correlations and usually produces waste heat. Storing and processing the data requires physical memory that eventually must be reset. Resetting memory, as argued in the late 20th century by people like Rolf Landauer and Charles Bennett, necessarily increases entropy in the surroundings. This is essentially the resolution that modern physics offers for Maxwell's demon as well. The demon in Maxwell's thought experiment was a tiny, intelligent being standing at a door between two volumes of gas, opening and closing it selectively to let fast molecules pile up on one side and slow ones on the other, apparently lowering entropy without expending work. For decades, the puzzle seemed to threaten the universality of the second law. When information theory entered thermodynamics, the demon's bookkeeping came under more careful scrutiny. To decide which molecules to let through, the demon must measure their speeds and positions. To implement a strategy, it must store and retrieve these measurements. Eventually, it must clear its records to make room for new ones. That erasure step, when analyzed as a physical operation on bits, has an unavoidable entropy cost. The net effect is that any decrease in entropy inside the gas can be offset, and usually exceeded, by the increase outside, in the demon's memory and in the apparatus that resets it. In this light, Loschmidt's reversal and Maxwell's demon are two versions of the same challenge. They ask whether, by being clever, one can beat the overall statistical drift toward disorder. The answer that emerges is that you can arrange brief, local decreases in entropy, and you can engineer echoes that look like fragments of the past returning, but only by pushing the entropy elsewhere even faster. There is no free lunch hiding in the fine print. Feynman liked these stories precisely because they force you to say where the arrow of time really resides. It is not located in any single collision, or in the shape of an equation, or in an absolute prohibition against certain microstates. It lives in the statistics of huge ensembles, in the special low entropy starting point of the universe, in the way we coarse-grained descriptions, and in the thermodynamic cost of acquiring, processing, and erasing information. From a philosophical angle, this is both reassuring and humbling. It is reassuring because it shows that dramatic-seeming paradoxes do not actually overturn the basic picture. The second law survives careful attacks. The apparent violations turn out to be cases where you have looked only at a subsystem and forgotten to count entropy in the machinery that manipulates it. It is humbling because it reminds you how limited our control really is. True Loschmidt reversals exist as mathematical possibilities, not as options on a laboratory menu, seen at the scale of a human life. This perspective clarifies something intuitive. You can indeed repair some of the damage from a bad decision. You can apologize, rebuild trust, clean up a mess, restore a building. In doing so, you impose new order on parts of the world. But you do this by investing resources, energy, and effort. You turn fuels into heat. You wear out tools. You age your own body. The local decrease in one kind of disorder is paid for by increases elsewhere. On balance, the global arrow still points the same way. At the cosmic scale, there is no super-observer outside the universe who can flip the velocities of all particles or orchestrate spin echoes for entire galaxies. There is no hand large enough to grasp every degree of freedom and make it run backward in perfect synchrony. The kind of delicate reversal that is barely achievable in a protected chunk of solid in a laboratory is, by construction, impossible for the whole. The universe is too big, too coupled, too noisy, so time does sometimes seem to fight back. Whenever clever thought experiments or real experiments try to force a reversal, they run into limits set by complexity, by coupling to environments, and by the physics of information. The harder you push against the arrow, the more clearly you see where it comes from. In the end, the picture that Feynman would likely endorse is not bleak. It does not say that everything decays, and that attempts at repair are meaningless. It says that repair is always partial and always costly, and that this is not a moral failing of the world, but a structural fact about how many ways its atoms can be arranged. You can reconstruct a fragment of order here, an echo of a signal there, a pattern in a brain that restores a memory. You cannot, even in principle, rewind the entire cosmic story to an earlier chapter. You might think of it in musical terms. From a few surviving notes and markings on old paper, a skilled musician can reconstruct a passage that was once played. They can bring back a phrase, a theme, perhaps even an entire movement. But the original performance, with all its contingent nuances and the exact arrangement of air vibrations in the hall, is gone as an accessible whole. The physics says that some shadow of it persists in the correlations of particles, but no one will ever gather those correlations up again. We can, in certain corners, coax an echo out of systems that seem to have forgotten. We can, for a while, push small pieces of the world up the entropy slope, but the full symphony of what has happened is not recoverable. And perhaps it is exactly this limit, this impossibility of a perfect undoing, that gives each moment its weight. If the future must live with the traces we leave, there is a darker question hiding underneath. Are there places in the universe where those traces can be erased, not just blurred, but stripped down to something that no longer remembers what produced them? Imagine someone standing at the edge of an accretion disk, at a safe distance but close enough to feel the pull in their bones. In their hands, a worn notebook, years of thoughts, confessions, sketches, the kind of private record that makes a life feel coherent. In a single motion, they throw the diary toward the black shape at the center. Gravity takes over. The pages tumble, catch light from the hot gas around the hole, and then vanish across the horizon. From the point of view of the outside world, that is the end of the object. The question is whether it is also the end of the information. For a long time, the easy answer in classical general relativity was yes. A black hole was defined by its event horizon, a surface beyond which no light and no signal could escape. Matter that fell in added to the total mass, charge, and spin, and nothing else about it mattered. The famous phrase was that a black hole has no hair. 1,000,000 different diaries, 1,000,000 different planets, 1,000,000 different people, once swallowed, all left the same simple imprint on the outside, just more of the same parameters. The detailed structure of what had fallen in seemed to be gone as far as the external universe was concerned. Then, in the early 1970s, Stephen Hawking calculated that this picture could not be so simple. By combining quantum field theory with the curved spacetime around a black hole, he found that black holes should not be perfectly black. They should emit radiation with a thermal spectrum, slowly losing mass over time. On March 1st, 1974, he published a paper in the journal Nature with the title Black Hole Explosions, and the question mark in that title has been haunting discussions ever since. If a black hole radiates like a hot coal, steadily spewing out particles in a nearly random pattern, then in the long run, it can evaporate completely. The horizon shrinks and disappears. What is left behind in the outgoing radiation appears, at least in Hawking's original calculation, to be purely thermal. That is, it carries no visible trace of the particular structures that fell in. If you throw in a diary, or a teacup, or an encyclopedia, the late-time radiation looks the same as if you had thrown in a cloud of featureless dust with the same total mass. Here is where the past begins to look endangered. Quantum mechanics, in its standard form, says that information about a system's state is preserved under time evolution. States can be scrambled and entangled, but there is always, in principle, some unitary map that takes initial states to final ones without losing detail. If a black hole takes many distinct initial states and turns them all into the same final state of outgoing radiation, that seems to violate this principle. It would mean that information is destroyed, not just hidden. From the perspective we have been building, this is not just a technical quarrel about equations. It touches the core question of whether the universe ever really forgets. If there truly exists a region where physical information disappears, not merely becomes inaccessible to ordinary observers, then the statement that the past never goes away would have to be softened. Black holes would be places where the universe itself allows erasure. The paradox sharpened as people followed the implications. If information is destroyed, then the usual rules for predicting outcomes in quantum theory break down. You can no longer think of the evolution as a reversible dance of amplitudes. Probabilities stop adding up in the neat way they should. On the other hand, if information is not destroyed, it has to go somewhere, and finding a consistent mechanism for that has proven hard. One way to visualize the dilemma is to return to the diary. before it falls in? You can, in principle, read every page. Even if you choose not to, the possibility exists. After it crosses the event horizon, no external observer can recover it. If the black hole then evaporates completely into a fog of thermal particles that carry no trace of the words, there is no way, even in principle, to reconstruct what was written. The text has been demoted from a low entropy pattern to undifferentiated noise. The arrow of time is woven deeply into this story. The formation of a black hole from collapsing matter is already an entropic process. Entropy increases. Hawking's result adds a new layer. The evaporation of the whole through radiation is a one-way transformation. The outgoing particles do not reconverge to form the exact structures that fell in. If information is truly lost, then the future is not just more disordered in the everyday sense. It is less informed. The mapping from past to future becomes many to one. That is why many physicists began to suspect that the original calculation, while capturing something important about black hole thermodynamics, could not be the full story. Somewhere in the description, perhaps beyond the reach of a simple quantum field treatment on a fixed background, there had to be a way for information to survive, even if in a form almost impossible to decode. The universe, in this view, might still refuse to let the past be wiped from its ledger. Popular culture has, in its own way, latched onto this intuition. In Interstellar, the character Cooper falls into a region representing the deep interior of a black hole, only to encounter a higher dimensional structure where time appears as a physical axis, lined with snapshots of his daughter's room. Gravity becomes a channel through which he can influence past events. The science in that sequence stretches and folds actual theory, but the emotional core is plain. People want to believe that ties of love and choice are not erased, even by the most extreme regions of space-time. Real physics does not offer secret libraries inside black holes where you can walk among your own history. It does, however, explore ideas that rhyme with the thought that information ends up stored in places we did not first expect. One of the most striking lessons of black hole thermodynamics is that the entropy of a black hole, a measure of how many internal microstates it could have, is not proportional to its volume, as you might guess, but to the area of its event horizon. In words, the more surface, the more ways the interior could be arranged, even though the outside world cannot see those arrangements directly. This proportionality between entropy and area led to the suspicion that whatever happens inside a black hole is somehow encoded on its boundary. That is, for an outside observer, all the information about the diverse things that have fallen in might be stored in degrees of freedom living on the horizon's surface. The original phrase, "no hair," becomes more nuanced. Black holes could have hair, but it is extremely fine, living in subtle correlations that are almost impossible to probe. From this seed grew the broader holographic principle. In certain theories of gravity, particularly those connected to string theory, there are concrete models in which a region of space-time with gravity can be described by a lower dimensional system without gravity living on its boundary. In those models, information is never lost. Processes that look, from the bulk space-time point of view, like things falling into a black hole and evaporating, correspond in the boundary theory to perfectly unitary evolution with no destruction of data. This correspondence is not a literal description of our universe. It is a laboratory of ideas, but it strengthens the hope that the past is not annihilated by black holes, only scrambled beyond recognition. The information paradox then becomes a puzzle about decoding, not about absolute deletion. Radiation that looks thermal in simple approximations might, on closer inspection, carry subtle correlations that, in principle, encode what went in. Attempts to make this picture precise have led to new questions. One of them is the firewall paradox. If information about what falls into a black hole is somehow imprinted on outgoing radiation, and yet the horizon is also supposed to be a smooth place for an infalling observer, tensions arise between different principles that we usually hold dear: the equivalence of gravitational and inertial frames, the unitarity of quantum mechanics, and the locality of interactions. Some arguments suggest that, to save information, the horizon might have to become a kind of energetic barrier, a firewall rather than a quiet crossing. Debates over firewalls, holography, and quantum gravity more generally are still active. What unites them is a refusal to accept that information can simply vanish. Physicists may be willing to modify their understanding of space-time at small scales, or to entertain radical new dualities between theories, but they are reluctant to give up the idea that the universe keeps track of its own states. Even in the darkest places, the accounting is believed to continue. It is here that the emotional and the technical threads meet. On a human level, there is a deep unease with the notion of being erased without residue. To be turned into noise is not just to die, but to be removed from the story altogether. The image of a diary being burned is harsh, but ashes and smoke at least remain. They can, in principle, be analyzed. The carbon atoms still exist, now part of other structures. The idea that a black hole might take all distinguishable patterns and return only featureless radiation feels like a more absolute kind of loss. Modern physics does not yet give a fully agreed-upon resolution, but the trend of thought, especially in approaches that unify gravity with quantum principles, leans toward a less nihilistic answer. The past, according to this emerging view, is not cancelled. It is transformed, encoded in ways that no realistic observer could hope to unpack, but not removed from the underlying state of the universe. From the standpoint of entropy, a black hole is an extreme storage device. Its entropy is enormous compared with that of ordinary matter of the same mass. That means there are fantastically many internal microstates compatible with the same external appearance. Each different combination of things that have fallen in could, in principle, correspond to a different internal configuration or to a different pattern on the horizon. The more matter the hole has swallowed, the larger its area, and the more capacity it has to hide distinctions. If we extend our earlier metaphor of the universe as a dusty room, a black hole is like a locked box in that room into which a vast amount of dust has been swept. From the outside, you may see only a smooth, featureless surface. Inside, the grains could be arranged in countless ways. When the box slowly leaks dust in a thin, steady stream, what trickles out looks random. Yet, if you could somehow track every grain and every faint interaction, you might find that the sequence of specks carries a complicated code describing what was once inside. For any ordinary purpose, the code is useless. No one will ever reconstruct a burnt diary from the heat radiation it gave off, and no one will reconstruct a fallen civilization from the Hawking radiation of the black hole that once consumed its star. The practical past is gone, but at the deepest level, if unitarity holds, something about those configurations has not been deleted. It has been woven into the structure of the outgoing field. So, even in the regions where our current theories wobble, the central Feynman question remains at the heart of the argument. Does the universe ever truly discard its own history, or does it only shuffle it into forms that are inaccessible to limited beings like us? Black holes are where this question becomes sharp, because they strip away almost everything except the most basic physical bookkeeping. By watching how physicists argue about them, about information, horizons, and holograms, you are watching a community wrestle with the idea of the past. The most extreme objects in the universe become mirrors in which we test our assumptions about memory and loss. They are dangerous not only because they tear apart matter, but because they force us to decide whether we believe in a cosmos that forgets. The answer, so far, is leaning toward a kind of stubborn remembrance. Not that our stories will be readable forever, but that they are never entirely unwritten. In the next step, we will walk away from event horizons and return to ordinary nights, to the scale of human actions and choices, and ask what it means to live in a world where the past, in some form, never really leaves. There is a night, somewhere in the middle of a busy life, when the house is finally quiet and a person sits alone at a table, lit only by a small lamp. Out of nowhere, or so it seems, a sentence returns. Something they said years ago, a careless phrase that cut deeper than they realized at the time. The moment is long gone, unreachable in every ordinary sense. But the consequence is still alive in another person, and in them, and in the shape of the relationship that grew around that impact. The physics of that moment is simple. Air vibrated. Patterns of sound carried energy to another nervous system. Hormones shifted. Habits of avoidance, or distance, or caution, slowly formed. The sentence took a few seconds to say, but it changed the configuration of a small part of the universe. The speaker can sit there now, in the quiet, and no amount of wishing will make those molecules rearrange as though it had never been spoken. This is where the arrow of time touches daily life most directly. Actions have the same irreversibility as spilled coffee or a shattered cup. You can sweep the floor, you can apologize, repair, compensate. You can surround the crack with new material. You cannot restore the exact earlier state. What you do instead is redistribute. You turn one pattern of damage into a different pattern of adjustment. In physical terms, the entropy generated by that interaction is still there, diluted into heat and microscopic motion. In human terms, the meaning is still there, held in memory and behavior. The second law says you cannot undo the overall increase in disorder, but you can take the energy you still have and build new order on top of the mess. A more careful pattern of words. A different way of listening. A promise kept over and over until it becomes part of the background. This is one reason Feynman's chalkboard arrows feel so strangely intimate. When he stood in a lecture hall in Cornell in the middle of the 1960s, drawing lines to represent time going this way or that, he was not only talking about gases and photons, he was pointing indirectly at the fact that we live in a universe whose temporal orientation was largely fixed by conditions we did not choose. The low entropy beginning, the smooth early cosmos, the long slope of increasing disorder that gives us stars and chemistry and brains. All of that is given. Within that given structure, our choices still matter. They are tiny nudges in the flow, but they leave marks. Feynman wanted his audience to feel that double truth. On the one hand, we arrive late in a story that was set in motion long before there were planets. On the other hand, our decisions carve small but real grooves in the local history, grooves that cannot be erased even if they can be softened. Popular stories have circled this theme for decades. In the film about the time-traveling teenager and the sports car, no one truly erases anything. The trip to the past creates a new version of events, but the original timeline still lives as memory inside the characters and as a layer in the narrative that the audience has already watched. In the film about the astronaut and the black hole, the protagonist does not wipe away what happened on Earth. He learns to see it from a different perspective and to act within the constraints it has set. In the film about inversion, the elaborate backwards choreography does not cancel the war it revolves around. It becomes one more twist in the same knot. These stories land with audiences because they quietly respect an intuition reality keeps enforcing. You cannot annul the past. You can only add to it. Even when a fictional universe allows characters to rewrite events, the act of rewriting itself becomes a new, inescapable layer of history. There is no clean slate, only more palimpsests. From the vantage point of entropy, you can turn this into a kind of ethics. If the world is always drifting from states with fewer possibilities to states with more, then the structures that matter most are the ones that resist, that drift for a while. A friendship that endures through difficulty. An institution that keeps knowledge safe across generations. A piece of music that is still played centuries after its composer died. A scientific insight that keeps showing up in new technologies. All of these are low-entropy islands, maintained with effort against the background tendency of things to fall apart. To create such structures is to spend energy in a particular way. You eat, you think, you talk, you move materials into place. You export entropy elsewhere, so that, in one corner, order can persist. A library has to be cleaned, catalogs updated, climate controlled. A community has to resolve conflicts, pass on stories, support the vulnerable. An artwork has to be restored, reinterpreted, played, and replayed. Nothing about this is free. It is precisely the cost that gives these structures their weight. Every choice you make is a small version of this. You can imagine each decision as a flick of ink into water. Once the drop leaves the brush, you cannot summon it back into the bottle. The molecules have already begun to diffuse. The simplest reaction is to say, the stain is there, and that is that. But you have another option, which is to keep painting. You can drag new lines through the spreading color, add other shades, change the flow of the water itself. In time, the blot becomes part of a larger pattern. It does not disappear. It becomes one element in a composition. In the physical world, there is no repainting that restores pure white. There is only the growth of more structure on top of what has already occurred. So the question shifts, not how can I erase my earlier strokes, but given the strokes that exist, what can I build now? The same holds for societies. History is full of catastrophes, injustices, and errors that cannot be undone. The task is not to pretend they did not happen, nor to imagine a timeline where they never occurred, but to decide what new arrangements can be built that acknowledge those facts and respond to them. The idea that the past never really goes away then has two faces. One is quietly comforting. It says that nothing is entirely without effect. Even small acts of kindness, brief flashes of understanding, or unnoticed moments of restraint write themselves into the world. They may not be remembered in detail, but they alter trajectories. Somewhere, some motions are different because you were here. The other face is demanding. It says that nothing is entirely harmless. Words spoken in haste, decisions made in indifference, systems designed without thought for those outside their boundary. All of these also persist. They become part of the environment future people will have to live in, just as we live with decisions made before we were born. The fact that fine-grained information is inaccessible does not excuse the coarse-grained impact. The title, Why the Past Never Really Goes Away, is, by now, not just a claim about physics. On the physical side, the reason is that entropy has been climbing from a remarkably ordered beginning. That climb ensures that there are stable structures in which records can be written. On the human side, the reason is that every action writes into networks larger than the individual. Social ties, institutions, ecosystems, even the climate. You might forget. The universe does not. Feynman's way of looking at this was not moralistic. He did not wave the second law like a finger of accusation. His stance was more like a kind of cultivated humility. We are small, he would say, but not negligible. The laws we have discovered so far do not single us out as central, yet our ability to understand them and to predict some of their consequences gives us a peculiar kind of responsibility. Sitting with that thought, you can return to the person at the table at night. The hurtful sentence cannot be unsaid. The configuration of atoms that carried it is gone, replaced by countless other configurations. But the relational pattern it helped create is still here. That person can now decide what to do with the time that follows. They can let the pattern harden into distance, or they can invest energy in reshaping it, action after action, in a direction that leaves a different legacy. On a grander scale, humanity as a whole is in a similar position with respect to the planet and to our own technologies. The past emissions are in the air. The past designs are embedded in infrastructure. The past algorithms are shaping habits. None of that can be rewound. But the next moves are still open. The low entropy beginning of the universe gave us a long stretch of time in which complexity could grow. How we use the remaining slope is up to us. So, an existential question hangs over the whole discussion. If the past does not vanish, but changes form and continues forward as patterns in matter and mind, in what form would you like your own traces to persist? As random noise in an already noisy field, or as threads in a story that someone else might one day retell? The physics does not answer this. It only tells you that you do not get to abstain. Doing nothing is itself a contribution to the way things unfold. You can picture a final scene in the lecture hall. Feynman stands in front of the blackboard, arrows of time sketched in every direction from some central point. Some arrows represent processes that are almost perfectly reversible at small scales. Others represent the one-way drift of entropy, the expansion of the universe, the decay of structures. He steps back and looks at the crowded board. Somewhere in that tangle, you are invited to draw your own small arrow, aligned not with fantasies of going back, but with a way of going forward that takes irreversibility seriously. The call, if there is one, is not to become anxious guardians of every microscopic consequence, but to become more deliberate authors of the macroscopic patterns we leave behind, to build organizations, relationships, and works that keep good information alive a little longer, to notice where our actions will write themselves most deeply into other lives, and to choose accordingly. If this way of thinking about time and memory resonates with you, you can carry it into your next ordinary decision, the next conversation, the next message you send, the next project you choose to begin. And if you want to keep exploring these questions, you can stay with this series. Share it with someone who also lies awake, wondering where their past has gone. And keep asking, together, what kind of traces you want to leave in a universe that never really forgets.